In the vast, dark expanses of our universe, where light years stretch into infinity, lies one of the most powerful phenomena known to science: neutron stars. These celestial objects are the remnants of massive stars that have gone through catastrophic supernova explosions. They are beautiful and terrifying all at once. But how did they form, and what is the terrifying power that they contain? Neutron stars are incredibly powerful and intriguing objects in the universe. Their story starts with the life cycle of massive stars, which are many times larger than our Sun. As these stars die, they explode spectacularly, creating a dramatic event called a supernova. This is the birthplace of neutron stars, which mark the transformation of a dying star into something extraordinary and bizarre. Massive stars spend millions of years burning nuclear fuel. Star undergoes a phenomenal transformation as its core collapses, releasing its outer layers into space in a supernova explosion, one of the most energetic events in the universe, because the energy produced by nuclear fusion exerts an outward pressure that counteracts the force of gravity pulling inward. This delicate balance keeps the star stable for the majority of its life. The core's atoms are compressed by the gravitational force, resulting in the combination of protons and electrons into neutrons. This dense ball of neutrons is called a neutron star. A neutron star can have a mass up to twice that of our Sun, but it is incredibly tiny, usually only about 20 kilometers in diameter. To put this in perspective, it's like pressing a mountain's mass into a space the size of a city. The collapse creates an object with staggering density. A teaspoon of neutron star material would weigh billions of tons on Earth. The gravitational force on the surface gravity of a neutron star is phenomenally strong, about 1 billion times stronger than Earth's. So even if you could stand on one, you'd be crushed to death and weigh 1 billion times more than you would on Earth. Two astronomers, Fritz Zwicky of Switzerland and Walter Bott of Germany, who worked at the California Institute of Technology, first postulated the existence of neutron stars in the 1930s, speculating that star formation could be caused by supernova explosions. Neutron stars are composed primarily of neutrons. This idea was revolutionary at the time because the idea of such dense objects was hard to understand. The work of Zwicky and Bott set the stage for subsequent studies that confirmed the existence of neutron stars. Studying neutron stars is challenging because of their small size and great distance from Earth. However, technological advancements have allowed astronomers to observe and understand more about these mysterious objects. Neutron stars are usually detected by the intense X-rays they emit, especially when they are part of a binary system. In these systems, the neutron star can pull matter from its companion star, heating it up to extreme temperatures and causing it to emit X-rays. The Chandra X-ray Observatory and the XMM Newton telescope are two of the most important modern observatories that use this phenomenon to study neutron stars. Astronomers study neutron stars in great detail thanks to radio telescopes, which detect pulsars, a type of neutron star that emits regular pulses of radio waves. Much like cosmic lighthouses, with their magnetic poles emitting radiation beams that sweep across the sky as the star rotates. Astronomers use these pulses as a guide to understand these high-energy phenomena. The Parkes Observatory in Australia and the Observatory in the United States played important roles in pulsar research until their respective collapses in 2020. In recent years, gravitational wave detectors like Virgo and Loki have opened up a new frontier in the study of neutron stars. When two neutron stars collide, they cause ripples in space-time called gravitational waves. These collisions are both impressive cosmic events and a goldmine of information about neutron star properties. Neutron-star merger in 2017 was a step forward in astronomy because it allowed scientists to study the event through gravitational waves and electromagnetic radiation. Neutron stars are like cosmic marbles. They have many layers, each with its own set of characteristics. At the center is the core, the densest part of the star. Around the core is the crust, which is less dense but still extremely compact when compared to Earth's atmosphere. Above the crust is the core of a neutron star is where the extraordinary happens. It is composed almost entirely of neutrons, which are subatomic particles found in atoms, and is compressed in a way that defies our everyday understanding of matter. The density is so extreme that a single cubic centimeter of neutron star core would weigh hundreds of millions of tons on Earth. The atmosphere surrounding the core is thin and wispy, interacting with space around it. Crust, which is dense but not quite as much as the core, it is composed of ions and electrons, but its density grows as one descends into the star, and its atomic composition is reduced to that of neutrons. This thin layer, which is only a few kilometers thick, is essential to the structure and behavior of the star. It is within this crust that the neutron star's magnetic field is located, which is among the strongest in the universe, with a strength that can reach 1 trillion times that of Earth's. Finally, the atmosphere sits above the crust, a layer that is. The atmosphere of a neutron star is a fascinating layer that is only a few centimeters thick. It primarily consists of hydrogen and helium, and is where the star interacts with its environment. The atmosphere can be extremely hot, reaching millions of degrees, and it emits radiation in the form of X-rays and other waves that our telescopes can pick up. The forces that prevent a neutron star from collapsing under its own gravity are based on principles from quantum mechanics, one of which is the neutron degeneracy pressure. Nuclear fusion reaction pressure stops neutron stars from collapsing into black holes, but quantum mechanics changes the game when it comes to neutron stars. The Pauli exclusion principle, a key idea in quantum physics, states that no two neutrons can be in the same state in the same space. This principle generates a force called neutron degeneracy pressure, which acts as a counterweight to gravity. Because neutron stars are so dense. On a neutron star, the force of gravity is so great that an object thrown 1 meter into space would collide with the surface at over 1,000 kilometers per second in less than a millisecond. To put this density into perspective, think of a sugar cube-sized chunk of neutron star material. It would weigh around 1 billion tons, or about the same as all the people on Earth put together. When you jump from Earth, you land gently on a neutron star, but when you jump from a neutron star, the force of gravity is. The nuclear reactions and quantum effects that take place inside neutron stars are unparalleled in both scale and intensity. The core of a neutron star is so dense that the neutrons are packed together, almost touching this state of matter called neutron dust, and the intense pull of a neutron star can bend light around it, a phenomenon called gravitational lensing. The neutron star's outer crust is fascinating in and of itself. It's made up of a lattice of atomic nuclei floating in an ocean of electrons. As one moves deeper into the star, the density rises and the nuclei become more packed together, eventually dissolving into a soup of neutrons and protons. In this inner crust, among other strange and exotic forms of matter, you can find free neutrons and components of the superfluid, which is one of the most fascinating aspects of neutron stars. Features of neutron stars include their magnetic fields, which can be 1 trillion times stronger than Earth's. These fields impact not only the star's atmosphere, but also the space surrounding it. In extreme cases, the magnetic field can even influence atomic structure, stretching atoms into thin, elongated shapes. Pulsars, a subset of neutron stars, are created when particles are accelerated to nearly the speed of light by this intense field. Stars that emit radiation pulses on a regular basis. This is due to the neutron star's rapid rotation and the radiation beams emitted by its magnetic poles, which act like lighthouses and sweep across the sky. When these beams point towards Earth, we detect a pulse. Pulsars are extremely accurate, with some rotating hundreds of times per second. They serve as cosmic clocks, allowing astronomers to measure time with incredible precision. Neutron stars are already remarkable, but some of them take it to a whole new level. These neutron stars, called magnetars, possess the strongest magnetic fields in the universe. Their fields are 1,000 times stronger than those of ordinary neutron stars and can reach a strength that is 1,000,000,000,000 times greater than Earth's. Magnetars are truly magnetic monsters, with their intense fields influencing every part of their being. The fields are so powerful that they can change the structure of atoms, stretching them into thin, elongated shapes due to the magnetic pressure. Magnetar storms, in which the magnetic field line snaps and reconfigures, releasing a huge burst of energy that results in a gamma-ray burst. One of the most energetic explosions in the universe can be observed from Earth. Star quakes, which are similar to earthquakes but far more powerful, can crack the crust of the magnetar and cause starquakes. Gamma-ray bursts can release massive amounts of energy in the form of gamma rays. On March 5, 1979, two Soviet spacecraft detected a powerful burst of gamma rays from a distant source. This event, now known as the March 5 event, was later determined to have originated from a magnetar in the Large Magellanic Cloud, a nearby galaxy. The burst was so intense that it momentarily blinded the spacecraft detectors. Since then, numerous more magnetar storms have been observed, each one providing critical insights into the nature of magnetars. Discover more about these extraordinary objects. One of the most well-known magnetar storms occurred on December 27, 2004, when a magnetar situated approximately 50,000 light-years away in the constellation Sagittarius released a gamma-ray burst so intense that it had an effect on Earth's atmosphere. Countless satellites and observatories worldwide picked up on this burst, demonstrating the tremendous energy output of magnetar storms and their ability to strike Earth from great distances. Are intriguing to study, but they also pose potential dangers. If a magnetar flared near Earth, the ozone layer could be stripped away, exposing the surface to dangerous UV radiation from the sun. This could lead to a huge spike in skin cancer and other health problems for living things. Additionally, the magnetic fields themselves could disrupt satellite communication systems and power grids, causing widespread technological failures. Thankfully, although magnetar storms are rare and none are currently close enough to Earth to cause an immediate threat, studying them helps scientists understand the risks and develop strategies to mitigate them. By observing and analyzing the effects of these storms, researchers can gain valuable insight into how these events could impact our planet. Despite the dangers, magnetars are intriguing objects because they provide a unique laboratory for studying physics. Studying magnetars allows scientists to test physics theories and explore new frontiers in our understanding of the universe. Additionally, magnetars play a role in the broader picture of the cosmos, as they are connected to other astrophysical phenomena like gamma-ray bursts and supernovae. By understanding magnetars, scientists can gain insights into the behavior of matter and the fundamental forces that govern the cosmos. Magnetars are an important part of our quest to understand the universe because they help us learn about star life cycles, supernova explosion dynamics, and gamma-ray burst mechanisms. Neutron stars are extremely energetic objects, and their energy dynamics are complex and fascinating. One defining feature of neutron stars is the radiation they emit, which spans the electromagnetic spectrum from radio waves to gamma rays. Neutron stars reveal a great deal about their interior workings and environments through their enormous radiation output, which is particularly noticeable in the X-ray and gamma-ray spectrums. In fact, one neutron star can be seen to be brighter than an entire galaxy in X-rays. This extreme radiation output is a result of the stars and its surroundings' intense magnetic fields, rapid rotation, and high temperatures, all of which contribute to the energetic emissions. Cosmologically speaking, neutron stars are radiation powerhouses. Unlike regular stars, which release the majority of their energy as visible light, neutron stars mainly emit radiation in the high-energy region of the electromagnetic spectrum. This difference in radiation output reveals interesting facts about the peculiar physical processes happening inside neutron stars. A neutron star's luminosity, or total amount of energy emitted per second, is directly related to its energy sources. One important source of energy for neutron stars is their W. The intense magnetic field of a neutron star causes charged particles to accelerate to nearly the speed of light, creating radiation beams known as pulsars. These beams periodically sweep across our line of sight, creating pulses of radio waves or other forms of radiation. Another important source of energy is the residual heat from neutron stars. Pulsars are neutron stars that spin hundreds of times per second. When a neutron star is formed from the collapse of a massive star's core, it is extremely hot and produces thermal emissions. These emissions, which can be detected by space-based telescopes, mainly take the form of X-rays. The amount of heat output from a neutron star can tell us a lot about its age and thermal history. Older neutron stars are cooler and emit less thermal emissions. Research into neutron stars' heat output has important implications for our knowledge of their structure and behavior. By deducing information about their core and crust, scientists can learn things like how fast neutron stars cool, which is dependent on the superfluid's properties and the crust's heat conductivity. Observations of neutron stars' thermal emissions also help with improving model predictions of their interiors and shed light on the exotic states of matter that can exist in such extreme environments. The study of neutron stars' magnetospheres is essential for understanding their energy dynamics because, as previously stated, their magnetic fields are among the strongest in the universe. When these fields interact with the neutron star surroundings, they create magnetospheres that are filled with charged particles. The interactions between the neutron star's magnetic field and these particles generate additional radiation, which adds to the neutron star's overall energy output. A neutron star in a binary system can accrete matter from its companion star, which is heated to extremely high temperatures and produces X-rays. The secretion process is another important source of energy for neutron stars and can result in phenomena like X-ray binaries and millisecond pulsars. Understanding the processes in which neutron stars generate energy is gravity's extreme playground. Neutron stars provide a window into the twisted and warped fabric of space-time, which is a natural laboratory for testing fundamental theories of physics and a key to unlocking many astrophysical mysteries. The extreme conditions in neutron stars push these theories to their limits, offering unique insights that cannot be obtained from any other object in the universe. One of the most intriguing features of these astronomical bodies is their involvement in the creation of gravitational waves, which are predicted by Albert Einstein's theory of general relativity. These waves are emitted by some of the most intense and powerful processes in the cosmos. One example is the gradual loss of energy caused by the gradual orbital motion of two neutron stars, which results in the emission of gravitational waves. In August 2017, the LIGO and Virgo observatories made a groundbreaking discovery in astrophysics with the first direct detection of gravitational waves from a neutron star collision. This event, known as GW 170817, confirmed the existence of gravitational waves and offered a new way to observe the universe. The two stars collided, releasing immense amounts of energy and sending powerful ripples through space and time. Various forms of electromagnetic radiation, such as gamma rays, X-rays, and visible light, were used to detect neutron stars. This simultaneous observation across different wavelengths ushered in multi-messenger astronomy, which allowed scientists to study the same cosmic event through multiple channels. The detection of GW 170817 gave valuable insights into neutron star nature and the extreme conditions in which they exist. From the collision, gravitational waves carried information about the masses and electromagnetic observations of neutron stars have shown the aftermath of the collision, which includes the production of heavy elements like gold and platinum in the intense environment of a neutron star merger. The tremendous gravitational fields close to neutron stars cause spacetime to distort significantly. This distorting is a crucial part of Einstein's theory of general relativity, which explains gravity as a transformation of mass from a constant to a quantum field. Extreme curvature of spacetime due to mass and energy near a neutron star manifests in various ways. For example, gravitational lensing bends light as it approaches the star, making the neutron star look enlarged or distorted when seen from Earth. Another consequence of the neutron star's proximity to Earth's gravitational field is time dilation. According to general relativity, time moves more slowly in stronger gravitational fields. This means that if Einstein predicted that In the vicinity of massive objects like neutron stars, time would pass more slowly than farther away. While this effect does not affect us on a daily basis, it becomes significant when we are close to these stars. Neutron stars also serve as a natural laboratory for testing Einstein's predictions regarding the behavior of matter and energy under extreme conditions. Scientists can test these predictions by measuring the precise timing of pulsars, which are rotating neutron stars. The study of neutron stars and their gravitational effects has deepened our understanding of general relativity and its implications for the universe. For instance, the double pulsar system, in which two neutron stars orbit each other, has offered some of the most rigorous tests of general relativity to date. Observations of this system have confirmed several predictions of the theory, such as the emission of gravitational waves and the resulting orbital decay. The study of neutron stars provides a glimpse into the universe's most exotic states of matter, including dense cores and exotic states of matter that are unlike anything on Earth. Scientists have been able to confirm many of Einstein's predictions and test the boundaries of his theory due to the extreme conditions near these stars. Under normal circumstances, protons and neutrons are composed of quarks held together by particles called gluons. However, under the extreme conditions found in the core of a neutron star, these nucleons may be broken down into their constituent parts, known as quark-gluon plasma. This bizarre and unusual state of matter challenges our current understanding of physics. The soup-like mixture of quarks and gluons is called quark-gluon plasma. It is believed to mimic the conditions immediately following the Big Bang, which gave us a window into the early universe. Both theoretical physics and experiments with particle accelerators like the Large Hadron Collider corroborate this theory. The latter set out to recreate the high-energy conditions needed to create QGP on a tiny scale, while the former shed light on the phenomenon through the study of neutron stars. Chance to study this matter state on a grander scale, shedding light on how matter behaves under extreme conditions. And another intriguing theory associated with neutron stars is the presence of strange matter. This strange matter is made up of quarks that are heavier than the up and down quarks that comprise ordinary matter. In the core of a neutron star, the pressure could be high enough to transform some of the quarks into strange quarks, creating a stable new form of matter. Although there is no direct evidence for strange matter at this time, the study of neutron stars offers a promising avenue for investigating this hypothesis. If strange matter does exist, it could have significant consequences for our knowledge of the basic forces at work in the universe, as it raises the intriguing possibility that entire stars could be composed of this exotic material. As we move outward from the center of the universe to the outermost regions of neutron stars, we come across another strange form of matter called nuclear pasta. Under the tremendous pressure of these stars' gravitational pull, atomic nuclei condense into shapes and structures that resemble different kinds of pasta, like spaghetti, lasagna, and NOI. The nuclei arrange themselves into layers, tubes, and other bizarre configurations. Nuclear pasta is more than just a funny name. It's a distinct phase of matter that tests our knowledge of nuclear physics. By studying nuclear pasta, we can learn more about how matter acts in extremely dense and pressure environments, which are hard to simulate on Earth. Nuclear pasta's unusual properties, like its great strength and electrical and thermal conductivity, have consequences for the thermal land. In terms of the magnetic properties of neutron stars, our understanding of their structure and behavior has been greatly enhanced by recent computer simulations. While theoretical models were the first to predict the existence of nuclear pasta, observations of neutron stars, especially their thermal emissions and magnetic fields, can help confirm and further elucidate these properties. As a result of their unique traits and behaviors, neutron stars and black holes, which are both formed from the remnants of massive stars that have used up their nuclear fuel, make intriguing astronomical study subjects. When a star significantly larger than our Sun runs out of fuel, its core collapses under the weight of its own gravity, resulting in a supernova explosion. A neutron star is formed when the core of a star, which can be as massive as 20 times the Sun's mass, collapses into a much denser state, similar to that of a black hole. The process of neutron star formation involves the compression of protons and electrons into neutrons, creating an extremely dense object. In contrast, black holes form when the gravitational collapse continues unchecked, compressing matter to an infinite density. There's a fundamental difference between neutron stars and black holes. Neutron stars have a surface, but it is extremely compressed, and their gravity is billions of times stronger. Black holes represent the point where normal physics breaks down and space-time is infinitely curved. The area surrounding a singularity, known as the event horizon, is virtually impenetrable. Compared to Earth's gravity, the impact of an object falling from 1 meter would be approximately 2,000 kilometers per second. However, given enough energy, it is theoretically feasible to escape the gravitational pull of a neutron star. On the other hand, black holes are so powerful that nothing, not even light, can escape their event horizon. Because their escape velocity at the event horizon is greater than the speed of light, black holes are essentially invisible and can only be detected through their interactions with the matter around them. Observing and distinguishing neutron stars and black holes requires knowledge of their distinctive characteristics. Pulsars, in particular, are identified by their periodic radiation pulses, which are generated as a result of the neutron star's rotation and spread out across the sky. X-ray telescopes are able to pick up on these pulses because of the high energy levels involved. Einstein's theory of general relativity predicted that time would behave differently in close proximity to black holes. Neutron star emissions, particularly in binary systems where the neutron star heats matter to extreme temperatures and emits X-rays. Black holes are generally not visible to the naked eye, but can be detected through their gravitational pull on nearby objects and their effects on the surrounding matter. For example, in a binary system, a black hole can form an accretion disk by pulling material from a companion star, which causes the material to be compressed and heated. Interstellar spirals produce powerful X-rays that can be detected by space telescopes. Another way to spot a black hole is to observe the stars in its orbit, which can be seen in the center of our galaxy with the supermassive Sagittarius, an asterisk gravitational wave. When neutron stars or black holes collide, they cause ripples in space-time, which observatories like Virgo and LIV can pick up on. A new era in astrophysics was ushered in 2017 with the first detection of gravitational waves from a neutron star merger, which validated numerous predictions regarding these objects. Similarly, the discovery of gravitational waves from black hole mergers has shed light on their characteristics and the nature of gravity. By comparing neutron stars and black holes, scientists gain a better understanding of the extremes of physics and the star life cycle. Both objects test our knowledge of matter, energy, and the basic forces that control the universe. The universe is filled with neutron stars, which shed light on the behavior of matter at nuclear densities. Black holes, with their event horizons and singularities, expand our understanding of gravity. Space-time is a cosmic light show where neutron stars emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. Among these emissions, X-rays are particularly important, as observed by powerful X-ray telescopes such as Chandra and XMM. The Chandra X-ray Observatory, one of the most advanced X-ray telescopes ever constructed, was launched by NASA in 1999. It has the unique capability to detect and image X-rays from high-energy regions of the universe, such as the remnants of exploded stars and regions surrounding neutron stars. Thanks to Chandra's sharp vision, astronomers have been able to study the intricate structure of neutron stars, which Newton has illuminated in vivid detail. Neutron stars, their environments, and the X-ray emissions from these objects have been studied by the European Space Agency's ESA mission XMM Newton, which has been operational since 1999 and has supplemented Chandra's X-ray capabilities. This collaboration has allowed scientists to gain a better understanding of the intense and dynamic processes at work in neutron star formation and evolution. Isolated neutron stars emit X-rays from their surface, which are heated to millions of degrees by magnetic and atonal processes or by the residual heat from the star's formation. In binary systems, neutron stars absorb matter from a companion star, which causes the infalling material to be heated to millions of degrees, emitting bright X-rays. Studies of neutron stars rely on these emissions, which reveal a great deal about the physical conditions and processes surrounding these stars. Spectroscopy, the study of emitted light, allows astronomers to deduce a neutron star's composition, temperature, density, and magnetic field strength by analyzing the X-ray and other radiation spectra. Spectroscopy of neutron stars involves dissecting the light into its wavelength components and identifying the distinct fingerprints of various elements and ions. This method has shown that neutron stars primarily contain hydrogen and helium in their atmospheres, with trace amounts of heavier elements. Neutron star mergers, in which two neutron stars collide and merge, are among the most energetic and dramatic events in the universe. The phenomenon known as NOA, a transient, is produced by these collisions. Spectral lines observed in X-rays can give precise measurements of the surface temperature and gravitational redshift, allowing scientists to probe the star's intense gravitational field. These observations help build a detailed picture of the neutron star's surface and its underlying structure. A kilonova is a spectacular explosion that lights up the electromagnetic spectrum. It's a result of the radioactive decay of heavy elements that were created during the merger of two neutron stars. The event is so rare that it awes the human eye. When the stars collide, they release a surge of gravitational waves and then a burst of gamma rays. As the material that was ejected from the collision cools and expands, it emits light across the electromagnetic spectrum, from ultraviolet to. The NOA was the first of its kind to be detected after the GW 170817 event in 2017. Gravitational waves from the neutron star merger were detected by Leo and Virgo, and within hours, telescopes all over the globe were focused on the source. The observations that followed gave a detailed view of the NOA, revealing the production of heavy elements like gold and platinum. This discovery confirmed that neutron star mergers are a major way that the universe gets its heavy elements. COVI aren't just pretty to look at. They also teach us a lot about the physics of these mergers, the characteristics of the ejected material, and the processes that create these elements. By analyzing their light curves and spectra, astronomers can improve their models of neutron star interiors and how matter behaves under extreme conditions. Neutron stars are fascinating remnants of massive stars and important players in the dramatic events called supernova. Stellar explosions are among the most energetic phenomena in the universe, and the formation of neutron stars is closely related to the dynamics of these powerful blasts. When a massive star runs out of nuclear fuel, it collapses catastrophically because it can no longer resist the pull of gravity. Then the star's outer layers are ripped off by shock waves sent outward by the rebound, which causes them to explode. The star undergoes a supernova explosion when its core is compressed to extremely dense conditions, creating a neutron star. The neutron star's presence in the core is essential to the process of the supernova explosion. The star's intense gravitational collapse and subsequent neutron star formation release a tremendous amount of energy, which powers the supernova explosion and sends the star's outer layers hurtling into space at tremendous speeds. The shock waves caused by this explosion. In a supernova explosion, the expanding gas shell and the newly formed neutron star both have a profound effect on their respective environments, as the shock waves from the explosion compress nearby objects, heating the interstellar medium and setting in motion the formation of new stars. This process enriches the galaxy with elements that stars and planets use, and it also triggers the formation of new stars. Intense radiation and winds from young neutron stars can energize the surrounding material, creating complex and beautiful structures known as supernova remnants. These remnants continue to impact their surroundings long after the initial explosion. Clouds of gas and dust, which could lead to the birth of new stars, are also distributed throughout the galaxy by these shock waves, which contribute to the chemical evolution of the galaxy. Studying supernova remnants, which can be seen in visible light, X-rays, and radio waves, helps astronomers understand the aftermath of stellar explosions. Neutron star remnants, on the other hand, are more compact structures formed by the explosion's shock waves and the ejected material. By comparing these two types of remnants, we can gain valuable insights into the nature of these explosions. Neutron star remnants, on the other hand, are the compact cores that remain after an explosion. These remnants, especially pulsars, emit radiation across the electromagnetic spectrum, which scientists can use to learn about the neutron star's properties and behavior. By studying neutron star remnants, scientists can probe the extreme conditions inside neutron stars, like their intense magnetic fields, and gain a better understanding of the explosion's dynamics and energy. Studying both the large-scale remnants of supernovae and the smaller-scale neutron star remnants provides a more complete picture of the stellar evolution and galactic impact of massive stars. Neutron stars are involved in supernovae in general, and they also contribute to cosmic events like gamma-ray bursts, the most energetic event in the cosmos, which are believed to be linked to specific kinds of supernovae, especially those in which massive stars collapse into black holes. The study of gamma-ray bursts associated with supernovae sheds light on the intense conditions and processes that take place during these devastating explosions. The remnants of neutron stars have a significant impact on galaxy evolution, changing its structure and composition as they release energy and heavy elements into the interstellar medium. Additionally, the shock waves from supernovae can initiate star formation, which in turn affects the birth and development of stars and planetary systems. The radiation and winds from neutron stars have a lasting impact on their surroundings, shaping the galaxy in dynamic and ever-changing ways. Neutron stars, formed from the remnants of massive stars in supernova explosions, are considered the architects of cosmic evolution. The study of neutron stars has a long and illustrious history, full of groundbreaking discoveries and theories that have deepened our understanding of these mysterious objects. In 1967, while collaborating with her advisor Anthony Hewish on a novel radio telescope to study K-earths, Jocelyn B. Burnell, a graduate student at the University of Cambridge, made a groundbreaking discovery. During her observations, Burnell detected what she first called scruff signals, which she described as sharp pulses of radio waves. This discovery ushered in a new era of astrophysics and laid the groundwork for decades of further research. This discovery, originally dubbed LGM-1 for Little Green Men, was later understood to be the emission from a rapidly rotating neutron star. These pulsars, so-called, emit radiation beams from their magnetic poles as the neutron star rotates. These beams sweep across space, creating the appearance of pulsing signals when they hit Earth. After careful analysis and ruling out various terrestrial sources of interference, Belle Burnell and her team concluded that the signals originated from space. Pulsars, which can be seen from Earth, gave astronomers a powerful new tool for studying neutron stars and testing the laws of physics in extreme environments. Jocelyn B. Burnell's discovery was a watershed moment in astrophysics because it proved that neutron stars, which had only existed in theory since the 1930s, were actually observable objects. This discovery sparked a flood of interest in neutron stars and their properties, and it also paved the way for lead to the discovery of numerous additional pulsars, each of which shed light on the peculiarities of matter's behavior in the presence of extremely powerful gravitational and magnetic fields. As our knowledge of neutron stars grew, so did the theories that surrounded them. At first, neutron stars were believed to be relatively simple objects made up primarily of neutrons. However, as more and more pulsars were studied, their complexity became apparent, and the possibility of extremely powerful magnetic fields inside them became apparent. Theoretical evolution has led to the discovery of magnets, which in turn has led to improvements in technology and observational methods. The study of neutron stars has also benefited from the launch of powerful space telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and the XMM Newton, which have enabled astronomers to observe neutron stars in greater detail. These fields are millions of times stronger than Earth's. Significant discoveries in the study of neutron stars including the detection of gravitational waves from new neutron star mergers like the GW 170817 event in 2017, have had a profound impact on astrophysics. These discoveries, made possible by the Virgo and LIGO observatories, have shown the complex structures and behaviors of neutron stars, from their hot surfaces to the dynamic interactions in their magnetospheres. The discovery of the first millisecond pulsar in 1982 was a major milestone. These neutron stars spin hundreds of times per second, making them among the fastest known. Research into millisecond pulsars has shed light on the spin dynamics of these objects. Another important finding is the multi-messenger observations of GW 170817, which included electromagnetic signals across the spectrum and offered a comprehensive view of the merger process and its aftermath. Neutron stars have been the subject of a steady stream of groundbreaking discoveries that have deepened our understanding of their evolution and the mechanisms that cause them to spin at extremely high speeds. These advancements have also shed light on neutron stars' roles in binary systems and the intricate interactions that can take place within these settings. From the initial theoretical predictions made by Fritz Zwicky and Walter Baade to the groundbreaking, through the insightful observations of Jocelyn Bell Burnell and the comprehensive studies made possible by modern telescopes, the scientific understanding of neutron stars has been continuously expanding, leading to profound philosophical contemplation. These dense remnants of a universe exist in a realm where the usual rules of physics bend and occasionally break, serving as a stark reminder of the universe's complexity and vastness. Neutron stars, with their incredibly high densities and powerful magnetic fields, serve as a stark reminder that the cosmos is not a placid, serene setting, but rather a constantly shifting, occasionally chaotic environment. The forces at work in and around these objects are on a scale that is nearly unfathomable, and stellar explosions raise deep, existential questions about our role in the universe and the very nature of reality. When we consider the implications of neutron stars, we are faced with the enormous scales of space and time. These stars can remain visible for billions of years after their creation, contrasting sharply with the ephemeral nature of human life. This contrast can make us reflect on the nature of existence and the transient nature of our own experiences in comparison to the vastness of space and time. While considering neutron stars, it is important to keep in mind that our everyday experiences only cover a small fraction of what the universe has to offer. The existence of these extremes challenges our understanding of matter and energy, demonstrating that the universe is capable of creating conditions far beyond what we encounter on Earth. As a result, we are forced to reconsider what is possible and push the boundaries of our knowledge. The study of neutron stars can bring about contemplation of our place in the universe and the wonders of our capacity for curiosity and discovery. It can also make us feel small because our planet is so tiny and because our existence is so fleeting compared to the vastness of the universe. As a whole, astrophysics and space exploration cultivate a cosmic view that can have far-reaching philosophical effects on Earthlings. By gazing up at celestial bodies like neutron stars, we can better comprehend the vastness and magnificence of the universe, which in turn inspires awe and curiosity, which in turn motivates us to seek explanations for our own origins and our role in the cosmos. In the face of immense difficulty, we persist in our quest for knowledge, which is a tribute to the indomitable human spirit and our natural curiosity about the universe. Scientific inquiry allows us to broaden our horizons and gain a better understanding of the cosmos, and our observations of neutron stars make us think about the interdependence of all things, including the elements that comprise our bodies and our planets were created in stellar furnaces and spread out across the galaxy by stellar winds. Understanding that we are literally composed of star material can help us feel more connected to one another and the cosmos as a whole. Looking at neutron stars and thinking about their characteristics can also make us appreciate how fragile and valuable life is. The harsh conditions found inside and around neutron stars make them uninhabitable for Earth-like life, highlighting how fragile life is. Understanding the delicate equilibrium necessary for life to persist can bring about a deeper respect for Earth's singularity and the significance of safeguarding the ecosystems that support it. Neutron star and black hole collisions are two of the most intense and spectacular cosmic events, with each producing unique gravitational wave signatures that provide light on the characteristics of these cosmic objects. The properties of neutron stars and black holes can be better understood through collisions, and we can gain insight into the processes of cosmic evolution and structure formation through the unique gravitational wave signatures produced by neutron star mergers. When two neutron stars spiral inward and eventually merge, the resulting waves reflect the complex interactions of these dense objects and are rich in detail. Display distinct characteristics, such as an in-spiral phase where the stars spiral inward at an increasing rate and a merger phase where the stars merge into one. The resulting gravitational wave signal is usually longer and more complex than that of black hole mergers. Detection techniques for these waves depend on extremely sensitive observatories, such as Virgo and LIGO, which measure minute distortions in space-time caused by passing gravitational waves. Signals from neutron star mergers can be. Gravitational waves from neutron star mergers are easily identifiable by their unique patterns of frequency and amplitude, which provide information about the masses and radii of the merging stars. By detecting these waves, scientists have been able to learn more about the inner workings of these dense objects. On the other hand, gravitational waves from black hole collisions tend to be shorter and less complex. When two black holes merge, they mostly release gravitational waves in the last moments of the merger. When two neutron stars collide, the result can be a hypermassive neutron star that may exist for a short time before collapsing into a black hole. This transient object can emit powerful electromagnetic waves during its in-spiral and merger phases, followed by a brief ring-down phase as the newly formed black hole settles into a stable state. The signals from neutron star mergers are typically lower in frequency and magnitude due to the larger and denser nature of neutron stars. In contrast, black hole mergers produce a single larger black hole and usually do not emit significant electromagnetic radiation, so they are mainly observed through gravitational wave observations. However, black hole mergers can also be characterized by the release of various types of electromagnetic radiation, such as gamma-ray bursts and Kylan and OI, as the debris from the collision is heated and ejected into space. Neutron star mergers produce heavy elements like gold and platinum, which contribute to the chemical enrichment of the galaxy. These elements are dispersed into the interstellar medium, where they undergo a process known as gravitational waves, which help confirm the properties of the final black hole, such as its mass and spin. Both types of collisions play crucial roles in cosmic evolution and the formation of structures in the universe, can eventually fuse with neutron stars to form new stars and planets. The discovery of CoV during neutron star mergers lends credence to this nucleosynthesis process, drawing attention to the cosmic significance of these events in the matter cycle. Black hole collisions, although not directly affecting chemical enrichment, impact galaxy dynamics and evolution. When black holes merge, they can eventually form supermassive black holes at galaxy centers, which are crucial in neutron stars and theories of everything. The extreme conditions found in neutron stars, such as immense gravity, density, and magnetic fields, provide unique opportunities to explore and potentially validate theories that go beyond standard physics. These efforts aim to regulate star formation and the overall structure of galaxies, as well as to influence the distribution of matter in the surrounding regions through gravitational waves caused by black hole mergers. Neutron stars, with their intense gravitational fields and dense matter, offer an ideal setting for testing theories of quantum gravity, which aims to reconcile the principles of quantum mechanics, which govern the behavior of particles at the smallest scales, with general relativity, which describes the gravitational force at the largest scales, in the elusive quest for a unified theory of everything. Neutron stars and the quantum gravity they exhibit pose formidable challenges to our current understanding of the universe. However, There is some indirect evidence regarding the behavior of gravity under extreme conditions that observations of neutrons, specifically their gravitational wave emissions, can provide. For instance, the accurate measurements of neutron-star collisions taken by observatories, such as Virgo and Leo, can test predictions made by theories of quantum gravity. Changes from general relativity that could point to new physics that explains how quantum gravity works. String theory is another theoretical framework that aims to bring all the basic forces and particles into harmony. In this theory, instead of point-like particles, the universe is built from tiny vibrating strings that can exist in different dimensions. The properties of particles and forces are determined by the vibrations of these strings, which in turn influence neutron stars and their extreme. Neutron stars, with their extremely high densities and powerful gravitational fields, may be able to influence or be influenced by these extra dimensions in ways that could be observable. For example, the behavior of matter and radiation near a neutron star could reveal subtle effects that indicate the presence of extra dimensions, while direct proof would be difficult to come by. Various speculative ideas involving neutron stars include beyond string theory, which suggests that spacetime has a discrete structure at the smallest scales, and loop quantum gravity, which postulates that exotic particles or forces exist. Neutron stars, with their unique conditions, provide a testing ground for these theories, which could reveal new aspects of the observable only in neutron stars. The extreme conditions within them serve as a link between the quantum realm and the macroscopic world of gravity, allowing scientists to better understand the interplay between the two realms. This quest for a unified theory of everything, which aims to integrate the basic forces of nature into a single framework, is one of the great challenges in physics. As part of our endeavors to bring all the fundamental forces into harmony, we need to figure out how gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force can all be explained by a single set of rules. Neutron stars, which are essentially composed of neutrons and are subject to intense gravitational fields, are ideal laboratories in which to study these interactions. By studying and modeling the behavior of matter in neutron stars, we can learn more about how these forces could be unified. Researchers can test predictions from different unification theories by studying neutron stars' internal structures. The matter inside these stars is so dense that it may be in a state that combines nuclear and gravitational physics. By understanding the equation of state, which describes how matter behaves at these densities, researchers can learn more about neutron stars and their contributions to unification efforts. The study of neutron star mergers and the gravitational waves that result from them has made a significant contribution. These events teach us a lot about how matter behaves under extreme conditions and about gravity itself. Precise measurements of these waves can test different gravity models and put constraints on theories that try to bring all the fundamental forces into harmony. Neutron stars, with their eerily powerful and unusual environments, are perfect test subjects for comparing neutron star jets and quasar jets, two of the most energetic and intriguing phenomena in the universe. We find that these two types of jets differ in their formation mechanisms, emission characteristics, and the forces that govern them. While both jets involve the ejection of matter at relativistic speeds close to the speed of light, our investigation into these fundamental questions in physics can shed light on the universe's deepest mysteries. Relativistic jets, which are powerful streams of charged particles ejected from the vicinity of compact astrophysical objects, have effects on their surroundings and provide unique insights into the various processes at work in the universe. Neutron star jets, on the other hand, are usually associated with pulsars or neutron stars in binary systems. In these systems, material from a companion star is directed onto the neutron star's magnetic poles, where it is accelerated along the lines of its magnetic field and expelled at nearly the speed of light. X-ray binaries are a common place to spot neutron stars interacting with their companions, which releases high-energy radiation in the form of quasar jets. In contrast, quasar jets are born in the area surrounding supermassive black holes in the galactic cores, where matter is heated and ejected along the black hole's rotational axis to create jets that stretch thousands of light years into space. These jets are propelled by a complex interplay between the black hole's magnetic field, accreting matter, and relativistic effects. Both types of jets travel at relativistic speeds, but quasar jets can reach higher velocities than neutron star jets because of the enormous gravitational forces at work. Despite their lower power, neutron star jets can still accelerate particles to significant fractions of the speed of light, and their high velocities cause relativistic effects like time dilation and the spectral signatures of neutron star jets provide information about the accelerated particles, the strength of the magnetic field, and the interaction between the jets and the surrounding material. Doppler shifting of the emitted radiation is essential for understanding the physical conditions inside the jets, and the emission characteristics of neutron star jets differ significantly from those of quasar jets. The spectral energy distribution of quasar jets can shed light on physical processes happening close to the supermassive black hole, like synchrotron radiation from high-energy electrons spiraling in magnetic fields and inverse Compton scattering, as well as on neutron star jets, which can exhibit periodic variations linked to the neutron star's rotation and orbital motion in binary systems. The process of relativistic electron-photon scattering involves accelerating low-energy photons to higher energies. Quasar jets, which can be seen as a reflection of the black hole's dynamic environment, are known for their rapid brightness and spectral property changes. The jet's profound impact on their surroundings varies between neutron stars and quasars, although neutron star jets are more powerful and have more localized effects. They can heat and ionize the material immediately around them, creating shock waves, and a quasar jet's enormous power and size allow it to impact star formation and gas distribution in the host galaxy, as well as produce large-scale structures called radios, where the expelled material interacts with the surrounding interstellar medium. It can also be observed as bright X-ray and radio sources, which provide information about the density and composition of the interstellar medium. Quasar jets are a key component of the cosmic ecosystem, and their study using observations across the electromagnetic spectrum sheds light on the processes that drive high-energy astrophysical events. These interactions can cause the formation of hotspots and shock fronts, which are visible as extended radio sources. Feedback from quasar jets can control the expansion of supermassive black holes and the evolution of galaxies. An intriguing candidate in the quest to understand one of the most profound mysteries of the universe is dark matter, which is an invisible substance that makes up neutron stars and quasar jets. Detailed observations of these objects have been made possible by the Hubble Space Telescope and a very large array, shedding light on their structures, dynamics, and impacts. It is extremely difficult to directly detect dark matter, which makes up around 27% of the universe. Instead, scientists infer its presence through its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light from distant stars. Neutron stars provide a unique environment to study and potentially detect dark matter, thanks to their extreme density and strong gravitational fields. One important question in this field of research is whether neutron stars can capture dark matter particles as dark matter. As matter particles travel through the galaxy, they can come into contact with neutron stars through gravity. Because of the strong gravitational pull of neutron stars, dark matter particles could be pulled into their interiors. According to theoretical models, neutron stars could eventually gather a lot of dark matter in their cores. If neutron stars manage to capture dark matter particles, it could have a lot of important effects, the most important of which would be on the thermal evolution of the star. Another consequence of dark matter accumulation in neutron stars is the possible impact on their structure and stability. If dark matter particles interact with regular matter, they could deposit energy inside the neutron star, changing its temperature and cooling rate. This energy deposition could lead to observable changes in the thermal emissions from neutron stars, which would be indirect evidence of dark matter interactions. Finally, dark matter particles could form a dense core within the neutron star, influencing its overall mass. And pulsars are neutron stars that spin fast and emit radiation pulses at regular intervals. If dark matter particles enter these stars and create a Bose-Einstein condensate, an exotic state of matter in which all of the particles occupy the same quantum state, then the star's observable properties, like its spin rate and magnetic field strength, could change. Pulsars could be used to detect these changes. The study of dark matter interactions with neutron stars is still in its early stages, but it holds great promise for advancing our understanding of both dark matter and neutron star physics observational methods. For example, the presence of a dark matter condensate could cause the star to exhibit new types of oscillations or instabilities, which could be detected as gravitational waves or changes in the star's rotational period. In order to find evidence of dark matter in neutron stars, scientists use sensitive instruments and keep an eye on them over time for any changes in their thermal emissions, rotational behavior, or gravitational wave signatures. Theoretical research is also important for understanding the possible interactions between neutron stars and dark matter, and computer models and simulations can help predict how dark matter could interact with neutron stars. Particles could act in the harsh environment of a neutron star. These models can direct observational strategies and explain observed anomalies. One active field of study is the idea that dark matter particles could annihilate inside neutron stars. If dark matter is composed of particles that can annihilate each other when they collide, this process could release a lot of energy, which could heat the neutron star and cause noticeable changes in it. Neutron star mergers, which create strong gravitational waves and electromagnetic signals, may also provide clues about dark matter. Any dark matter in the neutron stars would be subjected to extreme conditions during the violent merger process, which could lead to the discovery of new properties of dark matter. Finding Thal emissions that detect such heating effects would be strong evidence for the existence of dark matter. Researchers in the field of neutron star physics and dark matter are at the forefront of modern astrophysics. By studying neutron stars and how they interact with dark matter, they hope to gain a better understanding of these mysterious objects and the mysterious substance that shapes the universe. The quest to detect dark matter through neutron stars is a testament to the intense search for this mysterious substance. The extraordinary gravitational fields of neutron stars have a profound impact on the passage of time around these objects, providing researchers with a window into the universe's most fundamental mysteries. Space-time neutron stars, with their extremely dense interiors and powerful gravitational pulls, produce an environment where the consequences foretold by general relativity theory become extremely relevant. Examining these effects of relativity can shed light on time dilation and the fundamental structure of space-time, according to Einstein's general theory of relativity. Mass and energy cause gravity to act as both a force and a curvature of space-time. This curvature influences the rate of time travel, with stronger gravitational fields causing slower speed compared to weaker ones. This effect, known as gravitational time dilation, is particularly noticeable in the vicinity of massive objects, such as neutron stars, on the surface of a neutron star, the gravitational field is so powerful that it distorts space-time to an extraordinary degree. Anything close to the star appears to have time pass more slowly to an observer at a safe distance. This means that if you could somehow survive near the surface of a neutron star, you would age more slowly than someone far away from the star. This extreme dilation of time is a direct result of the intense gravity that characterizes these stellar remnants. To visualize this, consider the following. Thinking about gravitational wells, neutron stars form very deep ones because they are so dense and massive. The farther you go into one, the stronger the gravitational field and the more noticeable the time dilation at the surface. Since neutron stars are so massive, studying the effects of time dilation near them can teach us a lot about how the universe works. Time dilation around neutron stars can be studied in a number of practical ways, one of which is by observing pulsars, which are neutron stars that spin very quickly and release radiation beams from their magnetic poles as they pass Earth. This is a great way to test the limits of relativity and learn more about the fundamental interactions between time and gravity. By generating a regular pulsing signal, which can be measured with high precision, neutron stars can shed light on the structure of space-time surrounding them. For instance, if a neutron star is in a binary system with another star, the gravitational interaction between the two objects can alter the pulse timing, which can be studied to determine the effects of time dilation and the geometry of those objects. Space-time within the system. Such observations have given some of the most accurate tests of general relativity, proving its predictions with remarkable precision. The concept of space-time curvature, as described by the general theory of relativity's mass and energy curve, can be investigated through observations of neutron stars and their extreme gravitational fields, which affect the motion of objects and the passage of time. Very severe curvature can even cause light to bend significantly, an effect called. One way to study the effects of extreme gravity around neutron stars is through gravitational lensing, which involves studying how neutron stars' gravity bends and distorts light and other radiation. This allows scientists to map the curvature of space-time and learn more about the basic properties of gravity. Gravitational waves, which are ripples in space-time caused by the acceleration of massive objects, can also be observed through observatories like Virgo and Leo. The study of time around neutron stars not only enhances our understanding of these fascinating objects, but also informs our broader understanding of the universe, space-time curvature, and the dynamics of the merger. By analyzing gravitational wave signals, scientists can test the predictions of relativity and explore the behavior of space-time in extreme conditions. Studying these fundamental aspects of general relativity in the context of neutron stars provides important tests of this theory. These studies also help us understand how the universe works on both large and small scales, and the insights we get from studying neutron stars can have broader implications for our understanding of the cosmos. Neutron stars also test our assumptions about the nature of reality and the limits of our perception. Neutron stars are a testament to the extremes of nature. Their density is so high that a teaspoon of neutron star material would weigh billions of tons, and their gravitational field are so intense that they warp space-time. They push the boundaries of what we can observe and comprehend, revealing the limits of human perception and the vastness of the cosmos. The warping of space-time near neutron stars affects the flow of time and the path of light, creating phenomena that are hard to understand due to our everyday experiences. The idea that time can slow down or speed up depending on the strength of gravity, and that light can be bent by gravitational fields is beyond our comprehension, and it challenges our ability to imagine and comprehend such extreme states of matter and energy. The study of neutron stars has been greatly enhanced by the advent of highly sensitive instruments that can detect and study these objects across the electromagnetic spectrum. Telescopes, such as the Chandra X-ray Observatory and the Very Large Array, have allowed us to study neutron stars in unprecedented detail, providing images and data on their emissions. These observations have pushed the boundaries of what is technologically possible. The study of neutron stars also challenges our theoretical frameworks, as their extreme conditions, like high densities and strong magnetic fields, need models that go beyond standard physics. Understanding the behavior of matter at such high densities involves complex calculations and simulations, testing even the most powerful computers. This requires advanced detectors and precise calibration to capture the faint signals from distant neutron stars. Neutron stars show us the boundaries of our understanding, with their enormous size and energy levels making it hard to fathom how a star can collapse into an object as small as a few kilometers across, but with a mass greater than the Sun. The energies released during neutron star mergers are mind-boggling, and we rely on these theoretical models to make predictions and interpret observations. Studying neutron stars also brings to light the limits of our senses. Our eyes can only perceive a small fraction of the electromagnetic spectrum, but neutron stars emit radiation across a wide range of wavelengths, from radio waves to gamma rays. In order to understand this phenomenon, we depend on instruments and detectors that. The discovery of neutron stars and subsequent advancements in their study have transformed our understanding of stellar evolution and the life cycle of stars. Neutron stars represent a critical phase in the life of massive stars, and technological extensions of our senses allow us to observe the universe in ways that would be otherwise impossible. By studying phenomena that are far beyond our natural capabilities, we are able to uncover the hidden aspects of the universe, bridging the gap between supernova. The knowledge gained about supernova explosions, black holes, and other cosmic phenomena has far-reaching consequences for our view of the universe. It demonstrates that stars are born, live, and die in this vast, constantly evolving environment, and that neutron stars play an important role in this matter and energy cycle. Understanding this forces us to reevaluate our role in the cosmos, as the elements that comprise our bodies and the planet were formed in star cores and dispersed across the galaxy as a result of these explosive events. Astronomical phenomena are intrinsically linked to our own existence. This fact brings to light the interdependence of the universe and our role in it. And it serves as a sobering reminder that our universe is far more vast and intricate than we may have previously imagined. Neutron stars, which are celestial objects formed by the catastrophic collapse of massive stars, are both aesthetically stunning and terrifying. The beauty of neutron stars lies in the fact that they reveal the most intense forms of the fundamental forces of nature. They are a testament to the power of gravity, which can compress a star's core to a size similar to a small city while maintaining a mass greater than our sun. A teaspoon of neutron star material weighs billions of tons, and stars like these are fascinating laboratories of physics that push the boundaries of our understanding and challenge our perceptions of reality. Their radiation, particularly from pulsars and magnetars, is so intense that it can affect their surroundings across the galaxy, and their surface temperatures can reach millions of degrees. On the other hand, neutron stars evoke a sense of terror due to their extremely harsh conditions. Their magnetic fields are powerful, often trillions of times stronger than Earth's, and they produce exotic phenomena like magnetars. Interactions between neutron stars, which cause gravitational waves and kilonoi, release energies that are both astonishing and humbling, reminding us of the immense power within these tiny but mighty objects. Learning about neutron stars helps us understand the universe and our role in it, while studying stellar remnants reveals the violent and ever-changing processes that govern it. Neutron stars also show us how stars die and come back to life. In cosmic evolution, the elements formed in the supernova explosions and neutron stars are the building blocks of all life on Earth. In a fundamental way, we are all composed of star stuff, formed in the crucibles of stars that lived and died long before our solar system came into being. When we reflect on neutron stars, we gain a greater understanding of the complexity of the universe and our place in it. We also gain humility as we realize how insignificant we are in the grand scheme of things. In the grand scheme of things, it also motivates us to keep exploring and finding answers to the mysteries that surround us. The study of neutron stars is a perfect example of humanity's never-ending pursuit of knowledge and its desire to understand the basics of reality. Our journey to understand neutron stars is never-ending, and with each observation and theoretical advancement, we uncover more secrets about the universe. Advanced telescopes help us uncover even more of these secrets. We are able to study neutron stars in greater detail thanks to improved instruments, which in turn yields new data and insights. As we delve further into neutron star nature, we find more questions, which in turn spurs new research and exploration. Neutron stars, with their aesthetically terrifying nature, represent the complexity and grandeur of the universe. They captivate our imagination and inspire us to go beyond the familiar in our quest to understand the boundaries of matter and energy. As we delve further into this realm of extremes, we take with us the knowledge that the universe is expansive, dynamic, and full of mysteries waiting to be solved. I hope you liked this video and would like to thank you for subscribing and leaving a like. The continuous study of neutron stars promises to keep unveiling the mysteries of the cosmos, allowing us to marvel at the power and beauty that exists beyond our earthly experience. Thank you for tuning in.